Good evening. Tonight we're going on a journey with a single raindrop, from warm air above the forest to the ground where it returns to the earth. Our journey begins 1,000 meters above the forest, where a droplet forms in warm air. The transformation starts on the surface of a salt crystal, sodium chloride, microscopic, suspended in the afternoon cloud. This particle crossed an ocean as spray, dried in sunlight, travelled on winds for days before arriving here, above the trees, in the zone where water changes state. The crystal measures 10 micrometers across. Its surface is irregular, pitted with age, electrically charged. Water vapour accumulates on this charged surface. Molecules arrive, they settle, they bond. In the tropical atmosphere, moisture is abundant. The air temperature hovers at 24 degrees Celsius, warm by the standards of cloud formation, but cool enough. The humidity exceeds 100%. The air holds more water than equilibrium allows. This supersaturation drives condensation. Vapor must become liquid. Energy must be released. The phase transition is inevitable. Each water molecule approaching the salt crystal carries thermal energy, kinetic motion, the vibration of atoms that constitutes heat. When the molecule bonds to the growing droplet, when hydrogen finds oxygen and electromagnetic forces lock the structure together, that thermal energy transforms. Some becomes the latent heat of condensation, approximately 2.25 megajoules per kilogram, released into the surrounding air, warming it, making it more buoyant, feeding the convection that lifts the cloud higher. The cloud itself is a vertical structure. Its base sits at 800 meters above the canopy, where rising air reaches its saturation point. Its top extends to 3,000 meters or more, towers of cumulus building through the afternoon heat. Within this structure, currents move both up and down. Updrafts carry moisture from below. Downdrafts transport cooler air from above. The droplets forming within this turbulence are suspended, held aloft by rising air, growing as they rise. The salt crystal dissolves as the droplet grows. Sodium ions separate from chloride ions. Each ion becomes surrounded by water molecules, their polar nature orienting the hydrogen and oxygen atoms in specific arrangements. The positive sodium attracts the negative oxygen ends. The negative chloride attracts the positive hydrogen ends. The crystal structure disappears, replaced by dissolved ions distributed throughout the liquid volume. The salt has not vanished. It has dispersed, become part of the solution, altered the chemistry of the droplet in ways that will matter later. Growth proceeds molecule by molecule. The rate depends on supersaturation, on temperature, on the size of the droplet itself. Small droplets grow faster initially because their high curvature creates favorable conditions for deposition. But as size increases, as the surface area expands, the rate of growth per unit area decreases. The droplet must compete with millions of other droplets for the available vapor. The cloud's moisture is finite, distributed among countless growing spheres of liquid. At 20 micrometers diameter, the droplet contains approximately 4 million molecules. The mass measures approximately 4 picograms. The weight, the downward force of gravity, equals approximately 4 times 10 to the negative 14th newtons. This force is insignificant compared to the upward force of the updraft carrying the droplet skyward. The droplet rises, still growing, still accumulating mass from the vapor-rich air streaming upward from the forest below. The forest below is invisible from here, obscured by the cloud's own density, by the scattering of light through billions of water droplets. But the forest's influence is everywhere. The moisture condensing into this droplet was, moments earlier, transpired from a leaf, evaporated from soil, released from the river. The forest and the atmosphere are coupled, linked by the constant cycling of water. The trees release moisture that forms clouds. The clouds release rain that feeds the trees. The system is circular, self-sustaining, ancient. The droplet continues growing. 50 micrometers, 100. At 100 micrometers, terminal velocity begins to matter. The droplet's weight, though still tiny, is now sufficient to pull it downward against the updraft. The fall rate at this size is approximately 1 centimeter per second, negligible but real. If the updraft weakens, if the convection slows, the droplet will begin to descend. But for now, the updraft remains strong, perhaps 2 meters per second, far exceeding the droplet's fall rate. The droplet rises higher into the cloud. Temperature decreases with altitude. At 1,500 meters, the air temperature has dropped to 20 degrees Celsius. The cooling follows the saturated adiabatic lapse rate, approximately 6 degrees per 1,000 meters, slower than the dry adiabatic rate because condensation releases heat, partially offsetting the cooling. The droplet's temperature matches the air temperature. There is no temperature gradient between droplet and atmosphere, no driving force for heat transfer. The droplet is in thermal equilibrium with its environment, but growth cannot continue indefinitely through condensation alone. The vapor supply is limited. Other droplets are consuming the available moisture. The supersaturation is decreasing as more water condenses. The droplet needs a different mechanism to grow larger, to reach the size necessary to fall as rain. That mechanism is collision. The mechanism is geometric. Larger droplets fall faster than smaller ones. Differential settling brings them into proximity. When a large droplet overtakes a small droplet, when their surfaces touch, surface tension causes them to merge. The process is nearly instantaneous. 2 droplets become one larger droplet. The combined volume equals the sum of the original volumes. The combined surface area is less than the sum of the original surface areas. This reduction in surface area releases energy, making coalescence energetically favorable. The droplet measures 200 micrometers across. This size is critical. Below this threshold, droplets fall too slowly to overtake their neighbors effectively. Above this threshold, fall velocity increases rapidly with size, and collision rates accelerate. The droplet has crossed into the regime where coalescence dominates over condensation as the primary growth mechanism. The fall rate is now 1 meter per second. Smaller droplets, 50 or 70 micrometers across, fall at only 10 or 20 centimeters per second. The velocity difference means the larger droplet overtakes approximately 100 smaller droplets per second in a typical cloud. Most of these encounters do not result in collision. The airflow around the falling droplet deflects many smaller droplets aside. But the collision efficiency is not zero. Perhaps 10% of encounters lead to actual contact, 10 collisions per second, 10 coalescence events per second. Rapid growth. Each collision adds mass. A 70 micrometer droplet contains approximately 180,000 molecules of water. When it merges with the 200 micrometer droplet, the combined mass increases the diameter to approximately 210 micrometers. The percentage increase is small, only 5%, but the cumulative effect of many collisions is substantial. Within a minute, dozens of collisions occur. Within 5 minutes, the droplet has doubled in size. The collision process is not perfectly gentle. When 2 droplets collide at relative velocities of several meters per second, the impact creates oscillations. The merged droplet vibrates, deforming from spherical to oblate to prolate and back, surface waves traveling across the liquid. But surface tension is a powerful restoring force. The oscillations damp out within milliseconds. The droplet returns to its equilibrium spherical shape, or nearly spherical. At larger sizes, aerodynamic forces begin to flatten the bottom slightly. The collision efficiency depends on droplet size ratios. When a large droplet collides with a very small droplet, size ratio of 10:1 or greater, the collision efficiency is low. The small droplet tends to be swept around the large droplet by the airflow. When the size ratio is more moderate, 3:1 for instance, collision efficiency is higher. The small droplet's inertia carries it across streamlines, bringing it into contact with the larger droplet. Collision efficiency peaks at size ratios around 3:1, then decreases for nearly equal-sized droplets, which fall at similar speeds and rarely overtake each other. The droplet continues to fall and grow. 300 micrometers. 400. At 500 micrometers, half a millimeter, the fall rate reaches 3 meters per second. The updraft that was carrying the droplet upward has weakened. The droplet has risen high enough in the cloud that convection is less vigorous. The balance has shifted. The droplet is now falling relative to the surrounding air, descending through the cloud, still collecting smaller droplets as it falls. The cloud's vertical structure matters. Near the cloud base, droplet concentration is highest. More collisions occur here. Near the cloud top, droplets are fewer, more widely dispersed. The optimal growth zone is in the middle regions of the cloud, where droplet concentration remains high, but droplet sizes are already large enough for efficient coalescence. The droplet spends approximately 10 minutes in this zone, growing rapidly, accumulating mass from countless smaller neighbors. The trajectory through the cloud is not straight downward. Turbulence creates lateral motion, eddies that move the droplet sideways, up, down, in complex three-dimensional paths. But the overall trend is downward, pulled by gravity, accelerating as mass increases. The droplet traces a wandering descent through the cloud's interior, encountering different droplet populations, different moisture concentrations, different temperatures at different levels. At 600 micrometers, the droplet's shape begins to deviate measurably from spherical. Aerodynamic forces flatten the bottom surface. The pressure of air rushing past the falling droplet is higher on the bottom surface than on the top, creating an upward pressure gradient that deforms the droplet. Surface tension resists this deformation. But at this size and fall speed, aerodynamic forces are becoming comparable to surface tension forces. The droplet assumes an oblate shape, flattened on the bottom, rounded on top. At 700 micrometers, the droplet falls at 4 meters per second. Internal circulation is evident. The outer layers of water flow upward along the sides, across the top, downward through the center. This circulation is driven by shear at the air-water interface, by the drag of air moving past the falling droplet. The circulation rate is slow, perhaps 1 millimeter per second internally, but sufficient to mix the droplet's contents, to distribute dissolved salts and gases uniformly. The droplet encounters a region of downdraft. The cloud's internal circulation includes both updrafts and downdrafts. In this downdraft region, the droplet accelerates rapidly, its fall rate relative to the ground increasing from 4 meters per second to 7 meters per second. The enhanced fall rate brings it into more frequent contact with smaller droplets. Collision rate increases. Growth accelerates temporarily. Emerging from the downdraft, the droplet enters a region of weaker updraft. The fall rate relative to the air decreases, but the fall rate relative to the ground remains high. The droplet is near the cloud base now, approaching the transition to clear air below. At 800 micrometers, nearly 1 millimeter, the character of the droplet changes. This size marks a transition. Below 1 millimeter, droplets are small enough that they remain approximately spherical, dominated by surface tension. Above 1 millimeter, aerodynamic forces become significant, flattening the bottom, creating the classic raindrop shape. Not the teardrop of popular imagination, but an oblate spheroid, like a hamburger bun, flat underneath, rounded on top. The fall rate is now approaching 5 meters per second. The updrafts in the lower cloud are weakening. The droplet has descended to within 100 meters of the cloud base. The moisture content here is lower than in the upper cloud. Much of the water has already condensed, already fallen out as precipitation. Fewer small droplets remain available for collection. The growth rate slows, but the droplet has achieved critical size. Further growth is not necessary. At 1 millimeter diameter, with a fall velocity of nearly 6 meters per second, the droplet will fall through any remaining updraft, will exit the cloud base, will begin its descent through clear air toward the forest below. The final collisions occur in the lowest 100 meters of the cloud. Perhaps 20 more droplets merge with the original, adding incrementally to the mass. The droplet reaches 1.1 millimeters in diameter. The mass is approximately 650 nanograms. The weight is approximately 6.4 times 10 to the negative 12th newtons. Terminal velocity is 6.2 meters per second. The cloud base approaches. The droplet is among hundreds of thousands of similar droplets, all having grown through the same processes, all approaching rain size, all about to exit the cloud and begin the descent to the forest below. The rain shaft forming below the cloud is visible from a distance, a grey curtain of falling water connecting cloud to earth, the visible manifestation of the hydrologic cycle in action. Droplets merge through contact. This is coalescence, the collision-driven growth that transforms cloud droplets into raindrops. As opposed to our world, these collisions are beneficial. The mechanism is geometric. Larger droplets fall faster than smaller ones. Differential settling brings them into proximity. When a large droplet overtakes a small droplet, when their surfaces touch, surface tension causes them to merge. The process is nearly instantaneous. Two droplets become one larger droplet. The combined volume equals the sum of the original volumes. The combined surface area is less than the sum of the original surface areas. This reduction in surface area releases energy, making coalescence energetically favorable. The droplet measures 200 micrometers across. This size is critical. Below this threshold, droplets fall too slowly to overtake their neighbors effectively. Above this threshold, fall velocity increases rapidly with size, and collision rates accelerate. The droplet has crossed into the regime where coalescence dominates over condensation as the primary growth mechanism. The fall rate is now 1 meter per second. Smaller droplets, 50 or 70 micrometers across, fall at only 10 or 20 centimeters per second. The velocity difference means the larger droplet overtakes approximately 100 smaller droplets per second in a typical cloud. Most of these encounters do not result in collision. The airflow around the falling droplet deflects many smaller droplets aside. But the collision efficiency is not zero. Perhaps 10% of encounters lead to actual contact. 10 collisions per second. 10 coalescence events per second. Rapid growth. Each collision adds mass. A 70 micrometer droplet contains approximately 180,000 molecules of water. When it merges with the 200 micrometer droplet, the combined mass increases the diameter to approximately 210 micrometers. The percentage increase is small, only 5%, but the cumulative effect of many collisions is substantial. Within a minute, dozens of collisions occur. Within 5 minutes, the droplet has doubled in size. The collision process is not perfectly gentle. When two droplets collide at relative velocities of several meters per second, the impact creates oscillations. The merged droplet vibrates, deforming from spherical to oblate to prolate and back, surface waves traveling across the liquid. But surface tension is a powerful restoring force. The oscillations damp out within milliseconds. The droplet returns to its equilibrium spherical shape, or nearly spherical. At larger sizes, aerodynamic forces begin to flatten the bottom slightly. The droplet continues to fall and grow, 300 micrometers, 400. At 500 micrometers, half a millimeter, the fall rate reaches 3 meters per second. The updraft that was carrying the droplet upward has weakened. The droplet has risen high enough in the cloud that convection is less vigorous. The balance has shifted. The droplet is now falling relative to the surrounding air, descending through the cloud, still collecting smaller droplets as it falls. The cloud's vertical structure matters. Near the cloud base, droplet concentration is highest. More collisions occur here. Near the cloud top, droplets are fewer, more widely dispersed. The optimal growth zone is in the middle regions of the cloud, where droplet concentration remains high, but droplet sizes are already large enough for efficient coalescence. The droplet spends approximately 10 minutes in this zone, growing rapidly, accumulating mass from countless smaller neighbors. The trajectory through the cloud is not straight downward. Turbulence creates lateral motion, eddies that move the droplet sideways, up, down, in complex three-dimensional paths. But the overall trend is downward, pulled by gravity, accelerating as mass increases. The droplet traces a wandering descent through the cloud's interior, encountering different droplet populations, different moisture concentrations, different temperatures at different levels. At 800 micrometers, nearly 1 millimeter, the character of the droplet changes. This size marks a transition. Below 1 millimeter, droplets are small enough that they remain approximately spherical, dominated by surface tension. Above 1 millimeter, aerodynamic forces become significant, flattening the bottom, creating the classic raindrop shape, not the teardrop of popular imagination, but an oblate spheroid, like a hamburger bun, flat underneath, rounded on top. The fall rate is now approaching 5 meters per second. The updrafts in the lower cloud are weakening. The droplet has descended to within 100 meters of the cloud base. The moisture content here is lower than in the upper cloud. Much of the water has already condensed, already fallen out as precipitation. Fewer small droplets remain available for collection. The growth rate slows, but the droplet has achieved critical size. Further growth is not necessary. At 1 millimeter diameter, with a fall velocity of nearly 6 meters per second, the droplet will fall through any remaining updraft, will exit the cloud base, will begin its descent through clear air toward the forest below. 1 millimeter, the boundary between cloud and rain, a necessary distance. This measurement is not arbitrary, it reflects fundamental physics. Droplets smaller than 1 millimeter remain suspended indefinitely in moderate updrafts. Droplets larger than 1 millimeter fall as precipitation, descending even through strong convection. The 1 millimeter threshold marks the transition from cloud physics to precipitation physics, from suspended water to falling water, from potential rain to actual rain. The mass of a 1 millimeter spherical droplet is approximately half a microgram. The weight equals approximately 5 times 10 to the negative 12th newtons. Terminal velocity in still air at this size is approximately 4 meters per second, increasing toward 6 meters per second as the droplet grows slightly larger. These numbers define the droplet's fate. It will fall. It will descend through cloud base. It will emerge into clear air. It will become rain. The shape of the droplet has evolved. Surface tension still dominates. The droplet is not splitting, not fragmenting, but aerodynamic pressure flattens the underside. The bottom surface is nearly flat, sometimes even slightly concave. The top surface remains curved, approximately hemispherical. The overall shape resembles a hamburger bun more than the pointed teardrop often depicted in simplified illustrations. This shape is the equilibrium between surface tension pulling inward and aerodynamic pressure pushing upward on the base. Internal circulation develops at this size. As the droplet falls through air, friction at the surface creates shear. The outer layers of water begin to circulate, flowing upward along the sides, across the top, downward at the center. This circulation is slow, millimeters per second internally, but it mixes the droplet's contents, distributes dissolved salts evenly, maintains temperature uniformity. The droplet is not a static sphere of water, but a dynamic system with internal fluid motion driven by its movement through the atmosphere. The droplet reaches 1.2 millimeters in diameter. Growth has slowed dramatically now. Few cloud droplets remain in this lower region of the cloud to collect. Most water has already condensed and fallen. The droplet is among the last precipitation leaving the cloud, part of the trailing edge of the rain event. Other larger drops fell minutes earlier. Smaller droplets remain suspended above, still growing, not yet large enough to fall. The droplet represents the middle population, grown to precipitation size, now departing the cloud. The cloud base is approximately 800 meters above the forest canopy. The droplet is approaching this boundary, descending at 6 meters per second, about to emerge from the grey obscurity of cloud into the clearer air below. The transition will be abrupt. Within the cloud, the droplet is surrounded by other droplets, by suspended moisture, by near-saturated conditions. Below the cloud, the air is less saturated, clearer, warmer. The environment changes completely within a vertical distance of just a few meters. The moment of emergence arrives. The droplet crosses the cloud base, passing from the dense interior where visibility extends only meters, into the clearer air where visibility extends hundreds of meters. The visual transition is striking, though the droplet has no means to perceive it. The grey gives way to green. The forest, visible below, a vast carpet of vegetation, textured and layered, extending to the horizon. The canopy rises to meet the falling drop. This perspective inversion reflects reality. From the droplet's reference frame, the forest is accelerating upward, approaching at 6 meters per second. But in the Earth's reference frame, the droplet falls, pulled by gravity, air resistance balancing weight, terminal velocity established. The distance to canopy is 800 meters. At 6 meters per second, the transit time will be approximately 2 minutes and 20 seconds if conditions remain constant. But conditions will not remain constant. The air below the cloud differs from the air within. Temperature is higher, humidity is lower. These differences affect the droplet's journey. Evaporation begins immediately. The air below the cloud is unsaturated, its relative humidity perhaps 85% at this altitude. The vapor pressure in the air is less than the saturation vapor pressure at the droplet's surface. This gradient drives evaporation. Molecules at the droplet's surface gain sufficient thermal energy to break free from liquid phase, to overcome the hydrogen bonds holding them, to enter the vapor phase. The process is endothermic. Each molecule that evaporates carries away latent heat, cooling the droplet's surface. The evaporation rate depends on multiple factors: the humidity deficit in the air, the temperature, the size of the droplet, the velocity relative to the air. For a 1 millimeter droplet falling at 6 meters per second through air at 85% relative humidity, the evaporation rate is approximately 1 trillion molecules per second. This sounds catastrophic, but the droplet contains approximately 5 times 10 to the 17th molecules total. The fractional loss rate is approximately 0.2% per 100 seconds. The droplet will survive the 2-minute descent with most of its mass intact. The evaporation occurs preferentially from certain regions of the droplet surface. The bottom surface, moving through air at high relative velocity, experiences enhanced evaporation due to the continuous supply of fresh, unsaturated air. The top surface, in the wake of the falling droplet, experiences slower evaporation because the air there is more humid, enriched by evaporation from the droplet itself. This differential evaporation creates small temperature gradients within the droplet, but internal circulation mixes the water, maintaining nearly uniform temperature throughout. The cooling caused by evaporation is measurable. The droplet's temperature decreases from 23 degrees, the cloud-based temperature, to approximately 21 degrees within the first 30 seconds of fall. This cooling is transient. Heat flows from the warmer surrounding air into the cooler droplet, and soon thermal equilibrium is re-established. But the initial cooling is real, a consequence of the energy requirement of phase change. The heat transfer occurs through several mechanisms. Conduction transfers heat through the thin boundary layer of air immediately adjacent to the droplet surface. Convection transfers heat through the bulk airflow around the droplet. The relative contributions depend on drop size and fall velocity. For a 1 millimeter drop at 6 meters per second, convection dominates, accounting for approximately 80% of the heat transfer. The air through which the droplet falls is not still. Wind exists, moving horizontally at perhaps 3 meters per second in the mid-levels between cloud and canopy. This wind carries the droplet westward as it falls. The trajectory is therefore not vertical but slanted, a diagonal path through space. A droplet falling from 800 meters height, carried by 3 meters per second wind, will travel approximately 400 meters horizontally before striking the canopy. The landing zone is offset from the vertical projection of the starting point. Wind redistributes precipitation across the landscape. The wind velocity is not constant with altitude. Generally, wind speed decreases toward the surface due to friction with the ground and vegetation. At 800 meters altitude, wind speed might be 3 meters per second. At 400 meters, perhaps 2 meters per second. Near the canopy top, perhaps 1 meter per second. This wind shear affects the droplet's trajectory, creating a curved path rather than a straight diagonal line. Turbulence adds complexity. The atmosphere is never laminar at scales relevant to rainfall. Eddies exist, structures of rotating air, rising and sinking motions on scales of meters to tens of meters. As the droplet descends, it passes through these structures. Sometimes it encounters a downdraft, accelerating downward briefly before exiting into calmer air. Sometimes it passes through an updraft, slowing or even rising momentarily before resuming its descent. These perturbations create variability in fall rate, unpredictability in exact trajectory, but the overall trend remains downward. The droplet's wake structure is complex. As it falls through air at 6 meters per second, the air must flow around the droplet. The flow pattern depends on the Reynolds number, approximately 600 for a 1 millimeter drop at this velocity. At this Reynolds number, the wake is turbulent, characterized by vortex shedding, by oscillating flow patterns behind the droplet. The vortices shed alternately from opposite sides of the droplet, creating an oscillating wake, a pattern called a von Karman vortex street in fluid dynamics. These wake dynamics affect the droplet's stability. The oscillating forces from vortex shedding can cause the droplet to wobble, to deviate from a straight fall path, even to oscillate in shape. But for a 1 millimeter drop, the oscillations are small. Surface tension is strong enough to maintain shape stability. Larger drops, above 4 millimeters in diameter, become unstable and break apart due to these aerodynamic forces. But the 1 millimeter drop is stable, falling steadily. At 400 meters above canopy, the forest structure becomes discernible. The smooth green carpet seen from above resolves into individual tree crowns. Emergent trees are visible now, their tops rising above the general canopy level, their branches spread wide to capture sunlight. These trees are 60 meters tall, giants, their crowns 30 meters in diameter. The species vary. Dipterocarpaceae in Asian rainforests, Fabaceae in tropical Americas, Myrtaceae in Australia. But the structure is similar everywhere: emergent layer above, dense canopy layer below, understory in shadow beneath. The droplet can perceive, if perception were possible, the texture of the canopy. The surface is not uniform but lumpy, with the emergent crowns protruding like islands from the sea of lower canopy. The variation in height creates variation in impact points. Some droplets will strike emergent crowns at 60 meters height. Others will penetrate between emergents and strike the main canopy at 40 meters height. The vertical distance through canopy varies depending on exact landing point. The air warms as the droplet descends. Temperature increases at the ambient lapse rate, approximately 6 degrees per 1,000 meters. Descending 400 meters should warm the air by approximately 2.4 degrees. The droplet, in thermal equilibrium with the air, warms as well. The temperature approaches 24 degrees now, nearly matching the temperature at which the droplet first formed in the cloud above. The cycle is closing. The droplet began at altitude, descended, cooled, now warms again as it approaches the surface. Approaching 200 meters above canopy, the details sharpen further. Individual leaves become visible, at least in outline. The canopy is not a uniform surface, but a complex three-dimensional structure. Leaves layered at multiple heights, branches interwoven, gaps and holes where light penetrates. Some trees are deciduous, even in the tropics, losing leaves during dry seasons. Some are evergreen, maintaining foliage year-round. Some are flowering, bright colours, reds, yellows, whites, visible among the green. The diversity is immense, dozens of tree species in every hectare, hundreds across the forest. Birds fly beneath the droplet. A flock of parrots crosses below, squawking, their green plumage nearly invisible against the canopy background. They are moving toward a fruiting fig tree, following learned routes, exploiting the forest's resources. The droplet falls past their flight path, unseen by them, too small and fast to register in their visual fields. The final approach accelerates the perceived closure rate, 100 meters, 50 meters. The target leaf is not yet determined. The exact impact point depends on final trajectory, on small air currents near the canopy, on chance. But the general region is clear. The droplet is descending toward a section of canopy dominated by emergent dipterocarp trees, their large leaves horizontal, positioned to intercept rain, to channel water towards stems and roots. At 20 meters, the details sharpen dramatically. The leaf is visible now, 30 centimeters long, 15 centimeters wide, dark green with prominent veins, waxy cuticle reflecting sunlight. The leaf belongs to the uppermost branch of an emergent tree, exposed to full sun, positioned to capture both light and water. The droplet's trajectory intersects this leaf's surface. Impact is imminent, 10 meters. The leaf surface fills the field of view, if view were possible. The waxy cuticle is microscopically smooth, designed to repel water, to prevent colonization by algae and epiphytes, to maintain the leaf's function as a solar collector. Small imperfections are visible at this scale. Insect damage along one edge, a small patch of fungal growth near a vein, dust particles accumulated between rains. 5 meters, 3 meters. The droplet is committed now. No air currents at this range can alter the trajectory significantly. The impact point is determined, a location approximately 10 centimeters from the leaf tip, slightly off-center. The droplet approaches at 6 meters per second, its momentum substantial, its kinetic energy approximately 1.8 times 10 to the negative 8th joules. This energy must be dissipated in the collision. 1 meter, half a meter, the final instant of free fall. The air between droplet and leaf compresses slightly, creating a microscopic cushion of high-pressure air that marginally slows the impact. But the effect is negligible at these scales. Impact occurs, water meets leaf. The canopy rises to meet the falling drop, almost brushing its leafy hair against it. This perspective inversion reflects reality. From the droplet's reference frame, the forest is accelerating upward, approaching at 6 meters per second. But in the Earth's reference frame, the droplet falls, pulled by gravity, air resistance, balancing weight, terminal velocity established. The distance to canopy is 800 meters. At 6 meters per second, the transit time will be approximately 2 minutes and 20 seconds if conditions remain constant. But conditions will not remain constant. The air below the cloud differs from the air within. Temperature is higher, humidity is lower. These differences affect the droplet's journey. Evaporation begins immediately. The air below the cloud is unsaturated, its relative humidity perhaps 85% at this altitude. The vapor pressure in the air is less than the saturation vapor pressure at the droplet's surface. This gradient drives evaporation. Molecules at the droplet's surface gain sufficient thermal energy to break free from liquid phase, to overcome the hydrogen bonds holding them, to enter the vapor phase. The process is endothermic. Each molecule that evaporates carries away latent heat, cooling the droplet's surface. The evaporation rate depends on multiple factors: the humidity deficit in the air, the temperature, the size of the droplet, the velocity relative to the air. For a 1 millimeter droplet falling at 6 meters per second through air at 85% relative humidity, the evaporation rate is approximately 1 trillion molecules per second. This sounds catastrophic, but the droplet contains approximately 5 times 10 to the 17th molecules total. The fractional loss rate is approximately 0.2% per 100 seconds. The droplet will survive the 2-minute descent with most of its mass intact. The cooling caused by evaporation is measurable. The droplet's temperature decreases from 23 degrees, the cloud-based temperature, to approximately 21 degrees within the first 30 seconds of fall. This cooling is transient. Heat flows from the warmer surrounding air into the cooler droplet, and soon thermal equilibrium is re-established. But the initial cooling is real, a consequence of the energy requirement of phase change. The air through which the droplet falls is not still. Wind exists, moving horizontally at perhaps 3 meters per second in the mid-levels between cloud and canopy. This wind carries the droplet westward as it falls. The trajectory is therefore not vertical, but slanted, a diagonal path through space. A droplet falling from 800 meters height, carried by 3 meters per second wind, will travel approximately 400 meters horizontally before striking the canopy. The landing zone is offset from the vertical projection of the starting point. Wind redistributes precipitation across the landscape. Turbulence adds complexity. The atmosphere is never laminar at scales relevant to rainfall. Eddies exist, structures of rotating air, rising and sinking motions on scales of meters to tens of meters. As the droplet descends, it passes through these structures. Sometimes it encounters a downdraft, accelerating downward briefly before exiting into calmer air. Sometimes it passes through an updraft, slowing or even rising momentarily before resuming its descent. These perturbations create variability in fall rate, unpredictability in exact trajectory, but the overall trend remains downward. At 400 meters above canopy, the forest structure becomes discernible. The smooth green carpet seen from above resolves into individual tree crowns. Emergent trees are visible now, their tops rising above the general canopy level, their branches spread wide to capture sunlight. These trees are 60 meters tall, giants, their crowns 30 meters in diameter. The species vary: Dipterocarpaceae in Asian rainforests, Fabaceae in tropical Americas, Myrtaceae in Australia. But the structure is similar everywhere: emergent layer above, dense canopy layer below, understory in shadow beneath. The air warms as the droplet descends. Temperature increases at the ambient lapse rate, approximately 6 degrees per 1,000 meters. Descending 400 meters should warm the air by approximately 2.4 degrees. The droplet, in thermal equilibrium with the air, warms as well. The temperature approaches 24 degrees now, nearly matching the temperature at which the droplet first formed in the cloud above. The cycle is closing. The droplet began at altitude, descended, cooled, now warms again as it approaches the surface. At 200 meters above canopy, individual leaves become visible. The canopy is not a uniform surface but a complex three-dimensional structure, leaves layered at multiple heights, branches interwoven, gaps and holes where light penetrates. Some trees are deciduous, even in the tropics, losing leaves during dry seasons. Some are evergreen, maintaining foliage year-round. Some are flowering, bright colours, reds, yellows, whites, visible among the green. The diversity is immense, dozens of tree species in every hectare, hundreds across the forest. The final approach, 100 meters, 50 meters. The target leaf is not yet determined. The exact impact point depends on final trajectory, on small air currents near the canopy, on chance. But the general region is clear. The droplet is descending toward a section of canopy dominated by emergent dipterocarp trees, their large leaves horizontal, positioned to intercept rain, to channel water toward stems and roots. 20 meters. The details sharpen. The leaf is visible now, 30 centimeters long, 15 centimeters wide, dark green with prominent veins, waxy cuticle reflecting sunlight. The leaf belongs to the uppermost branch of an emergent tree, exposed to full sun, positioned to capture both light and water. The droplet's trajectory intersects this leaf's surface. Impact is imminent. 10 meters, 5 meters. The leaf surface fills the field of view, if view were possible. The waxy cuticle is microscopically smooth, designed to repel water, to prevent colonization by algae and epiphytes, to maintain the leaf's function as a solar collector. The droplet approaches at 6 meters per second, its momentum substantial, its kinetic energy approximately 1.8 times 10 to the negative 8th joules. This energy must be dissipated in the collision. Impact occurs. Water meets leaf. The collision is brief, violent by droplet standards, transformative. The leaf surface is hydrophobic. The waxy cuticle, a layer of long-chain hydrocarbons covering the epidermis, minimizes water adhesion. Contact angle between water and wax approaches 90 degrees, sometimes exceeds it, meaning water beads rather than spreads, forms spherical drops rather than films. This property evolved to shed water quickly, to prevent the leaf from becoming waterlogged, to allow photosynthesis to continue even during rain. The impact creates a splash. The droplet's kinetic energy exceeds the surface tension forces holding it together. Upon striking the leaf, the droplet deforms, spreading into a thin disc, perhaps 5 millimeters across. The deformation occurs in milliseconds. Then surface tension reasserts itself, pulling the water inward, attempting to minimize surface area to reform a sphere. But the process is incomplete. The impact energy was high enough to fragment the original droplet into several smaller droplets, one large drop containing 60% of the original mass, and 3 or 4 smaller drops containing the remainder. The largest drop, now approximately 900 micrometers in diameter, rests on the leaf surface. Surface tension and adhesion hold it temporarily. The leaf is oriented at approximately 20 degrees from horizontal, sloping downward toward the leaf tip. Gravity exerts a component of force parallel to the leaf surface. The drop begins to slide. The motion is not smooth. At the microscopic scale, the leaf surface is structured. Stomata, pores for gas exchange, dot the epidermis, each one approximately 20 micrometers across, surrounded by guard cells. These stomata are closed during rain, sealed to prevent water from entering the leaf's internal air spaces, but their presence creates surface irregularities. Trichomes, small hairs, protrude from the surface in some species, creating roughness, increasing the contact angle, enhancing water repellency. Veins, vascular bundles conducting water and nutrients, create ridges on the underside of the leaf, channels on the upper side. The sliding drop encounters these features, its motion jerking, catching and releasing as surface features alter the balance between gravity and friction. The drop accelerates as it slides. The angle is steep enough that gravitational force overcomes the resistance. The velocity reaches perhaps 5 centimeters per second by the time the drop arrives at the leaf edge. The distance traveled is approximately 15 centimeters, half the length of the leaf. The transit time is 3 seconds. During this slide, the drop oscillates slightly, its shape deviating from perfect spherical, responding to the forces acting upon it. The leaf belongs to Shorea leprosula, a dipterocarp species common in Southeast Asian rainforests. The leaf is 18 centimeters long, 9 centimeters wide, with a prominent drip tip, an elongated pointed apex designed specifically for water shedding. This adaptation is common in rainforest plants, allowing rapid drainage, preventing water accumulation that could promote fungal growth or block light from reaching the leaf surface. The leaf tip is pointed, extending perhaps 2 centimeters beyond the widest part of the leaf blade. Water accumulates briefly at the tip, held by surface tension, forming a pendant drop. The drop from the leaf surface merges with this pendant drop, adding mass, destabilizing it. The pendant drop now weighs approximately 3 micrograms, with a diameter of approximately 1.3 millimeters. The weight exceeds the surface tension forces holding it to the leaf tip. The pendant drop falls. The new journey is only 3 meters, the distance to the next leaf layer, where the canopy is densest, where leaves overlap in a continuous green shield against rain. The fall takes approximately 7/10 of a second. The drop accelerates under gravity, reaching a velocity of approximately 3 meters per second before striking the next leaf. This second leaf belongs to a different tree, Dryobalanops aromatica, another dipterocarp. The leaf is broader, 22 centimeters long, 12 centimeters wide, positioned horizontally rather than angled. The drop strikes near the leaf center. The impact is similar to the first: splash, fragmentation, reconstitution. But this leaf surface has slightly different properties. The cuticle is thicker, the wax density higher, the contact angle larger. Water beads more readily here. The reconstituted drop, now approximately 800 micrometers after losing some mass to fragmentation, sits as a nearly perfect sphere on the leaf surface. The horizontal leaf provides no gravitational component to initiate sliding. The drop sits motionless for several seconds. Then a breeze, minor air movement within the canopy, perhaps 5 centimeters per second, pushes the drop laterally. The drop rolls across the leaf surface, maintaining its spherical shape, moving toward the leaf edge at perhaps 1 centimeter per second. The distance is 11 centimeters. The transit time is 11 seconds. The drop reaches the edge and falls again. The third impact occurs on a compound leaf, a palm frond, belonging to Iguanura walliciana, an understory palm. The frond is divided into multiple leaflets, each narrow, 3 centimeters wide, 20 centimeters long. The drop strikes one of these leaflets at a glancing angle. The impact is gentler because the drop's trajectory was not perfectly vertical. The drop does not fragment, but deforms, spreads momentarily, then rebounds into spherical shape. The rebound actually lifts the drop momentarily off the leaf surface, a small hop, perhaps 2 millimeters high, before it settles back. The narrow leaflet provides a steep slope. The leaflet is oriented at 45 degrees from horizontal, angling downward. The drop slides rapidly, accelerating to 10 centimeters per second, reaching the leaflet tip in 2 seconds. The pendant drop formation is quick. The fall is short, only 2 meters to the next layer. The pattern repeats. Each impact, each fragmentation and reconstitution, each slide or roll across a leaf surface, each pendant drop formation, each fall to the next layer. The droplet, now more accurately described as droplets, plural, since the original has split into multiple pieces, descends through the canopy layer by layer. The fifth leaf is covered with epiphytes. Mosses grow on the upper surface, forming a green mat perhaps 3 millimeters thick. When the drop strikes this moss-covered surface, the behavior changes entirely. The moss is absorbent, porous, hydrophilic rather than hydrophobic. The drop does not bead or slide. Instead, it is absorbed, wicked, into the moss structure, distributed through the tiny spaces between moss leaves and stems. The water spreads through the moss, becoming part of the moisture stored there, available to the moss for photosynthesis, eventually to be re-released by evaporation or to drip off the moss when saturation is reached. But some water does drip immediately. The moss is already wet from previous rain. Additional water overloads its capacity. A small drop, perhaps 300 micrometers, forms at the lower edge of the moss patch and falls. This drop is now separate from the original droplet, a distinct entity, but containing water molecules that were part of the original, maintaining the connection through shared history. The 6th through 10th impacts follow similar patterns. Leaves of various species, Macaranga triloba with large leaves and prominent veins, Dipterocarpus grandiflorus with thick waxy cuticles, Ficus benjamina with smooth dark green leaves, Lithocarpus elegans with leaves covered in fine golden brown hairs on the underside, Artocarpus integer with deeply lobed leaves. Each species presents different surface properties, different angles, different challenges for the descending water. Some leaves channel water deliberately. Gutters formed by leaf edges, channels created by prominent veins, all direct water towards specific drip points. These adaptations prevent water from accumulating randomly on the leaf surface, direct it instead to controlled release points, allow the leaf to shed water efficiently without sustaining damage from water weight. The light continues to dim as descent proceeds. At the canopy top, illumination was approximately 1,000 watts per square meter, full tropical sunlight. At 10 meters depth into the canopy, illumination has dropped to 300 watts per square meter. At 20 meters depth, 100 watts per square meter. The spectrum shifts increasingly toward green as red and blue wavelengths are absorbed by chlorophyll in the leaves above. Temperature remains relatively stable. The canopy interior is buffered from temperature extremes. While the upper canopy leaves in full sun may heat to 35 degrees Celsius, the interior maintains a constant 26 degrees. The drops experience this stable temperature environment, neither warming nor cooling significantly during the descent. Humidity is high throughout the canopy. Transpiration from millions of stomata releases water vapor continuously. The air in the canopy interior holds moisture levels of 90 to 95% relative humidity. Evaporation from the drops is minimal. Water is conserved during this descent phase. The drops retain nearly all their mass, losing water only through the thin films left behind on each leaf surface contacted. The 15th impact strikes a bromeliad. This epiphyte, Guzmania lingulata, grows on a tree branch at 25 meters height. The plant's leaves form a rosette, creating a central cup that collects water. When the drop strikes a leaf near this cup, it slides down the leaf surface, which is channeled specifically to direct water into the cup. The drop enters the cup, a small pool perhaps 50 milliliters in volume, inhabited by mosquito larvae, tree frog tadpoles and various aquatic insects. The drop could remain here for days, part of this suspended aquatic ecosystem, but the cup is nearly full, and the additional water from rain causes overflow. Water spills over the lowest point in the cup's rim, forming a small stream that runs down the outside of the bromeliad, drips off the plant's base, and continues falling. The 20th impact, 25 meters below the initial impact, strikes a palm frond in the lower canopy. This frond belongs to Selaca conferta, a palm with pinnately compound leaves, each leaflet narrow and arranged along a central raches. The drop strikes, fragments across multiple leaflets, reforms partially, and drips off multiple points simultaneously. The water is now distributed among perhaps 6 or 8 small droplets, each 200 to 400 micrometers in diameter. These drops fall through the increasingly open structure of the lower canopy. At 30 meters above ground, the canopy transitions to understory. Leaves are sparser. Vertical distances between leaf layers increase from 1 or 2 meters to 3 or 4 meters. Free fall distances are longer. Drops accelerate to higher velocities between impacts. A drop strikes a broad-leafed understory shrub, Psychotria elata. The leaves are large, 25 centimeters long, positioned to capture the limited light that reaches this depth. The drop splashes on impact but reconstitutes, slides down the leaf following a prominent central vein that acts as a channel and drips off the tip. Final descent through the understory proceeds rapidly. Leaves are few. Open space dominates. Drops fall freely for 5, 7, even 10 meters between occasional contacts with understory vegetation. The drops are approaching terminal velocity between these contacts, approximately 5 meters per second for drops of this size. The forest floor becomes visible 15 meters below. Brown leaf litter, fallen branches, the occasional herbaceous plant adapted to deep shade. The final drop falls these last 15 meters without obstruction, accelerating, approaching the ground at 5 meters per second. The 20-minute journey through the canopy is complete. What began as a single 1 millimeter drop striking the uppermost leaf has become multiple smaller drops, distributed over perhaps 10 square meters of forest floor, but all descending in the same general area, all about to arrive at the ground within seconds of each other. The ground receives water, but ground is an imprecise term here. The surface is not soil, not mineral matter, but organic, a thick accumulation of dead leaves, fallen branches, decomposing wood, the forest's own waste recycled into its foundation. The leaf litter is layered by age and decay. At the surface lie freshly fallen leaves, recently detached from trees above, still retaining their form, their veins visible, their shapes recognizable. These leaves are brown, dry, or damp depending on recent weather, but not yet decomposed. They will lie here for weeks or months before fungi and bacteria break down their cellular structure. The drop strikes one of these fresh leaves. The impact is gentle. The drop has fallen only a few meters since leaving the last palm frond, its velocity limited, its kinetic energy small. The dead leaf flexes slightly, absorbing the impact, then springs back. The drop rests on the leaf surface, held by surface tension, a small sphere of water atop brown organic matter. The leaf is porous. Unlike living leaves with their protective cuticles, dead leaves have lost their waterproofing. Fungal hyphae have penetrated the epidermis. Bacteria have colonized the internal spaces. The leaf structure is compromised, perforated, absorptive. Water wicks into the leaf, drawn by capillary forces, spreading through the degraded tissue. The drop's spherical shape collapses as water is absorbed. What was a discrete droplet becomes a wet spot, the water distributed through the leaf's structure rather than sitting atop it. The molecules spread, diffusing through interconnected pore spaces, soaking into cellulose fibers, filling voids. The transition from droplet to moisture is complete within seconds, but the leaf itself is tilted, lying on an uneven substrate of older leaves beneath. Gravity pulls the water downward through the leaf. Water molecules on the underside of the leaf contact the layer below, wet that surface, begin to wick into the second leaf. The percolation has begun. Water moving downward through the litter layers, through the organic matrix, toward the mineral soil beneath. The litter is approximately 10 centimeters thick at this location. Below the fresh surface layer lies partially decomposed material. These leaves fell months ago. Their structure is softening. The veins remain visible but weakened. The leaf tissue is dark brown, colonized extensively by fungi. White mycelial threads, fungal hyphae, web through the structure, digesting cellulose, releasing nutrients, breaking down complex molecules into simpler forms that plants can absorb. Water moves through this layer slowly. The porosity is high. Perhaps 60% of the volume is void space, air-filled when dry, water-filled when wet. But the pores are small, interconnected through tortuous paths, creating resistance to flow. The water molecules diffuse, moving from pore to pore, following paths of least resistance, gradually working deeper into the litter. The temperature in the litter is stable, insulated by the canopy above and the soil below, buffered by the thermal mass of organic matter. The litter maintains a constant temperature of approximately 25 degrees Celsius. The water, arriving at 26 degrees from the warmer air above, cools slightly to match the litter temperature. The thermal equilibration is rapid, complete within seconds. Life pervades the litter. At scales invisible to the human eye, bacteria coat every surface. Perhaps 10 trillion cells per gram of material. These decomposers digest organic matter, breaking bonds, releasing carbon dioxide, recycling nutrients. Some are aerobic, requiring oxygen. Some are anaerobic, functioning where oxygen is scarce. All contribute to decomposition, to the transformation of leaves into humus, into mineral nutrients. Fungi are equally abundant. Their hyphae thread through the litter in networks kilometers long per cubic meter. These fungal networks connect trees, transferring nutrients between individuals, creating what some researchers call the wood wide web. The mycorrhizal fungi form partnerships with tree roots, exchanging absorbed nutrients for photosynthetically produced sugars. The saprotrophic fungi decompose dead material, recycling carbon, releasing nitrogen and phosphorus. Larger organisms inhabit the litter as well. Springtails, tiny six-legged arthropods, typically 1 to 2 millimeters long, leap through the pore spaces on specialized forked appendages. They feed on fungi, on bacteria, on decomposing material, themselves becoming food for predatory mites and beetles. Their population density can exceed 100,000 individuals per square meter in tropical rainforest litter. Mites crawl through the water films coating surfaces. These arachnids, often less than 0.5 millimeter long, are incredibly diverse, with hundreds of species in a single square meter of forest floor. Some graze on fungi, some prey on nematodes and other mites, some feed on decomposing leaves. All contribute to the ecosystem, to the nutrient cycling, to the energy flow from detritus to consumers. Millipedes burrow through the deeper litter layers. These arthropods, some species 10 centimeters long, have dozens of legs, move in slow, rippling motions. feed on decomposing leaves. They are detritivaries, essential participants in decomposition, breaking down large pieces of organic matter into smaller fragments that bacteria and fungi can process more easily. Their fecal pellets contribute to soil formation, to the gradual transformation of litter into humus. Earthworms are less abundant here than in temperate forests, but they exist. Tropical species, adapted to the warm, moist conditions, burrow through the litter and upper soil, consuming organic matter, excreting nutrient-rich casts. Their burrows create channels, preferential flow paths for water and air, improving soil structure. The water continues percolating downward. The molecular motion is driven by gravity, by capillarity, by the endless tendency of water to seek lower elevation. Individual molecules move along concentration gradients, diffusing from regions of high water content to regions of lower water content, but the overall motion is downward, through the layers, toward the soil. The lowest litter layer is well decomposed, almost soil-like in texture. The material is dark brown, almost black, its origin as leaves barely recognizable. This is humus, the end product of litter decomposition, rich in organic carbon, chemically complex, essential for soil fertility. The water reaches this layer, wicks through it, begins to contact the mineral soil beneath. The mineral soil is clay and silt, fine-grained, derived from weathered bedrock. The soil's red-brown color indicates iron oxide content, a product of intense tropical weathering. The texture is smooth, almost slippery when wet, the particles so fine that individual grains are barely distinguishable. The soil is already moist, nearly saturated from previous rainfall. Water enters the soil, filling the pore spaces between mineral particles. The flow is slower here than in the litter. Soil pores are smaller, resistance is higher, but the path continues downward. Some water is absorbed by tree roots. Some continues deeper, joining groundwater. Some flows laterally, moving down slope through the upper soil, seeking the lowest topographic position. The drop's identity has dissolved. It is no longer a discrete entity, but distributed moisture, spread through organic matter and soil, mixed with water from other drops, from yesterday's rain, from last week's storm. The molecules persist. Water is water. H2O is H2O. But the individual drop no longer exists as a unit. The decomposition process is not uniform across the litter layer. Hotspots of activity exist where conditions are particularly favorable, where moisture is high, where fresh organic matter has recently fallen, where fungal colonies are particularly vigorous. These hotspots can have decomposition rates 10 times higher than adjacent areas just centimeters away. The spatial heterogeneity creates a patchwork landscape at the millimeter scale, areas of rapid transformation adjacent to areas of relative stability. Temperature affects decomposition rates. At 25 degrees Celsius, the reaction rates of enzymes involved in decomposition are near optimal for many tropical species. Q10, the factor by which rates increase with each 10-degree temperature rise, is typically around 2 for biological processes. A 5-degree increase in temperature can increase decomposition rates by approximately 40%. This temperature sensitivity means that tropical forests, with their consistently warm temperatures, have much faster nutrient cycling than temperate or boreal forests. The leaf litter depth varies with location. In flat areas where leaves accumulate without being washed away, depth may reach 15 centimeters. On slopes where water movement is greater, depth may be only 5 centimeters. Near streams, where periodic flooding removes accumulated organic matter, litter may be absent entirely, exposing mineral soil. The spatial variation in litter depth creates variation in hydrology, in nutrient availability, in microhabitat conditions. The invertebrates in the litter are incredibly diverse. A single square meter may contain hundreds of species of mites, dozens of species of springtails, multiple species of beetles, ants, termites, and other arthropods. The diversity rivals that of the canopy, though at a much smaller scale. Each species plays a role. some shredding leaves, some preying on other invertebrates, some dispersing fungal spores, some aerating the litter through their burrowing activity. The litter is also home to vertebrates. Salamanders hunt for invertebrates in the moist organic matter. Frogs hide during the day, emerging at night to forage. Snakes, particularly small species, hunt the abundant lizards and frogs. Mammals like shrews and small rodents burrow through the litter, creating additional channels for water movement, contributing to the physical structure of the forest floor ecosystem. Time passes. Minutes become hours. The water moves slowly through the soil matrix. Water seeps through the forest floor, moving laterally now, following the slope, seeking the valley bottom where streams form, almost like a cross-country skier. The soil is structured at multiple scales. At the macroscopic scale, tree roots create channels, fallen logs create barriers, stones create impermeable obstacles. At the microscopic scale, mineral particles, clay, silt, sand, pack together with spaces between them, creating a network of interconnected pores. Water moves through this network, following the path of least resistance, seeking lower elevation. The pore sizes vary enormously. In clay-rich soil, pores may be only a few micrometers across, barely larger than the water molecules themselves. In sandy soil, pores can exceed 1 millimeter. The raindrop's water is distributed through pores of all sizes, some molecules in tiny clay pores, others in large sand pores, all moving generally downslope. The flow through pores is governed by Darcy's law, which relates flow rate to hydraulic gradient and hydraulic conductivity. The hydraulic conductivity depends on pore size distribution, on soil structure, on moisture content. Saturated soil has higher conductivity than unsaturated soil because air-filled pores do not conduct water. The upper litter and soil layers are nearly saturated after rain, facilitating relatively rapid lateral flow. The water molecules move by different mechanisms in different pore sizes. In large pores, bulk flow dominates. Water moves en masse, driven by pressure gradients. In small pores, capillary action becomes important. Water is pulled through narrow spaces by surface tension forces. In the smallest pores, adsorption onto mineral surfaces dominates. Water molecules stick to clay particles, forming bound layers that move very slowly if at all. The roots encountered earlier were actively absorbing water. The absorption process is complex. Water in soil has a certain potential energy determined by its elevation. By matrix forces, adhesion to soil particles. By osmotic forces, dissolved salts. Water in the plant xylem has lower potential energy due to the tension created by transpiration. Water flows from higher to lower potential, from soil into roots. The root hairs provide the interface. These single-celled extensions from the root epidermis have thin walls permeable to water. Water crosses the cell membrane by osmosis, driven by the concentration gradient of dissolved substances. The root hair cell has higher solute concentration inside than the soil water outside. Water flows in, down the concentration gradient, toward lower water potential. Once inside the root hair, water moves toward the xylem through two pathways. The apoplastic pathway involves movement through cell walls, through the spaces between cells, without crossing cell membranes. The symplastic pathway involves movement through the cytoplasm, through plasmodesmata, connections between cells, crossing multiple membranes. Both pathways converge at the xylem, where water enters the vascular system and begins its ascent to the leaves. The amount of water absorbed by roots is substantial. A large forest tree may transpire hundreds of litres per day. All that water must be absorbed from soil, pulled from the pores, transported through roots, lifted through the trunk, distributed to leaves. The forest floor is a vast absorption surface, millions of fine roots extracting moisture continuously, competing for the available water. But not all water is absorbed. Much flows through the root zone without being intercepted. This is the water that will eventually reach streams, that will become runoff, that will leave the hill slope and enter the drainage network. The proportion of rainfall that becomes runoff versus absorption depends on rainfall intensity, on soil moisture conditions, on root density, on many factors. The water continues moving downslope through the litter. A millipede burrow provides a preferential pathway. The millipede, Orthoporus texicolans, is a detritivore, feeding on decomposing leaves, creating tunnels as it moves through the litter. These tunnels are perhaps 5 millimeters in diameter, lined with compacted organic matter, providing channels for rapid water movement. Water enters the tunnel, accelerates. The resistance to flow is much lower in the open tunnel than in the surrounding porous litter. Flow velocity increases from micrometers per second to millimeters per second. The tunnel conducts water efficiently downslope, bypassing the slow percolation through organic matter. The tunnel intersects a layer of more decomposed material. Here, at 5 centimeters depth, the litter is dark brown, almost black, thoroughly colonized by fungi. White mycelial mats coat surfaces. Brown rot fungi are breaking down cellulose, leaving behind lignin-rich residue. White rot fungi are breaking down both cellulose and lignin, completely degrading the wood structure. The decomposition is advanced, the material transformed from recognizable leaves to amorphous organic matter. Water percolates through this layer more slowly than through the fresh litter above. The pores are smaller, the structure more compacted, but the moisture-holding capacity is higher. This layer acts as a sponge, absorbing water during rain, releasing it slowly during dry periods, buffering the hydrologic response of the forest floor. The water encounters a termite nest. The nest is embedded in the litter, constructed from fecal pellets and salivary secretions, formed into a hard structure resistant to water. The termites are fungus-growing species, cultivating fungal gardens inside their nest, feeding on the fungi, maintaining a complex agricultural system at miniature scale. The nest is impermeable. Water cannot penetrate the hardened walls. The flow diverts around the nest, following the path of least resistance along the nest's exterior. The nest acts as an obstacle, similar to the fallen log encountered earlier, creating temporary ponding on the upslope side, channeling flow around its perimeter. Emerging from behind the nest, water continues downslope. The slope steepens slightly here. The hill slope is not uniformly graded but has variations, subtle changes in angle that affect water movement. Steeper sections promote faster flow. Gentler sections allow pooling, temporary storage. The litter transitions to mineral soil. The boundary is gradual, organic matter mixed with mineral particles in a transition zone, but eventually the mineral soil dominates. Clay, silt, and fine sand derived from weathered bedrock, forming the substrate beneath the organic layer. The soil's color is red-brown, indicating iron oxides, products of intense tropical weathering. The clay mineralogy is dominated by kaolinite and iron oxides, low in nutrient holding capacity but stable in the acidic tropical environment. The soil pH is approximately 4.5, acidic due to organic acids from decomposition and lack of base cations leached away by heavy rainfall over millennia. Water enters the mineral soil through macropores, a root channel where a fine root died and decomposed, leaving a cylindrical void approximately 2 millimeters in diameter. Water flows through this channel preferentially, bypassing the tighter soil matrix. The macropore connects to other macropores, to cracks between soil aggregates, forming a network of fast pathways through the soil. This preferential flow is important hydrologically. During intense rainfall, water can move rapidly through macropores, reaching streams quickly, creating fast hydrologic response. Without macropores, all water would flow through the soil matrix, much slower, creating delayed response. The macropore network allows forests to shed water efficiently during storms, while still maintaining high soil moisture between rains. The forest floor is not flat. Tree roots create irregular surfaces, hummocks and depressions. Fallen logs lie across the slope, creating barriers. The terrain undulates at scales of centimeters to meters, and these undulations control water flow. Water accumulates in depressions, flows around obstacles, moves gradually downhill through the path of least resistance. The soil is structured. Roots pervade the upper layers, creating macropores, channels where roots once grew or where roots currently exist. These root channels are larger than typical soil pores, millimeters in diameter rather than micrometers, and water flows through them preferentially. The root channels form a network, interconnected, providing fast pathways for subsurface flow. The water molecules move through this network. The flow rate is perhaps 10 micrometers per second, slow by any standard, but faster than diffusion alone would allow. The driving force is the hydraulic gradient, the difference in potential energy between upslope and downslope locations. Water at higher elevation has higher potential energy. Water flows from high potential to low potential. The flow is inexorable, continuous, downslope. The path is complex. A molecule entering a root channel may travel several centimeters before the channel ends, blocked by soil or by a living root. The molecule then diffuses through smaller pores until it encounters another macropore channel and resumes faster flow. The overall path is tortuous, winding, but the net direction is downslope. Fungal hyphae create barriers and pathways. These microscopic threads, typically 2 to 10 micrometers in diameter, are coated with hydrophobic proteins. Water tends to flow around hyphae rather than through or over them. A dense hyphal mat can act as a barrier, channeling water along its surface. But hyphal networks also create structure in the soil, maintaining pore spaces that might otherwise collapse, facilitating drainage. The water encounters a beetle-larva burrow. The larva is a scarab beetle, perhaps 3 centimeters long, living in the soil, feeding on decomposing roots. Its burrow is approximately 5 millimeters in diameter, lined with compacted soil, open to water flow. Water enters this burrow, flows through it rapidly, perhaps 1 millimeter per second, much faster than through the surrounding soil. The burrow acts as a drain, collecting water from the adjacent soil, conveying it downslope efficiently. The burrow intersects a tree root. The root is approximately 1 centimeter in diameter, covered with fine root hairs. These root hairs are the actual absorption structures, single elongated cells extending from the root epidermis, increasing surface area enormously. Each root hair is approximately 10 micrometers in diameter, 1 millimeter long. A single centimeter of root may have thousands of root hairs, creating meters of absorptive surface. Water in the burrow contacts these root hairs. The root is absorbing water continuously, driven by transpiration in the leaves high above. The xylem vessels in the root are under tension, negative pressure, pulling water from the soil. The root hairs provide the interface where soil water enters the plant. Some water molecules are absorbed. They cross the cell membrane of the root hair, enter the cell's cytoplasm, move through cell walls and membranes toward the xylem, then ascend through the vascular tissue toward the trunk, toward the branches, toward the leaves, where transpiration creates the tension that drives the entire system. Within hours, these molecules will be transpired from stomata, returning to the atmosphere, beginning the cycle again. But most water molecules continue in the burrow, flowing downslope, bypassing the root. The root can only absorb water at a finite rate. Excess water flows past, continues downslope, joins the subsurface flow that will eventually emerge as seepage or spring flow. The water exits the burrow at the downslope end, enters the soil matrix again, continues percolating. The flow slows, the path becomes more tortuous. But the direction remains downslope, always downslope, driven by gravity, by the hydraulic gradient, by the fundamental principle that water seeks the lowest available elevation. A fallen log lies across the slope ahead. The log is perhaps 30 centimeters in diameter, 3 meters long, lying where it fell during a storm years ago. The log is decomposing slowly, colonized by fungi, riddled with insect borings. The exterior is soft, easily crumbled. The interior retains some structural integrity but is no longer solid wood. Water moving downslope through the soil encounters the log. The log acts as a barrier. Water accumulates on the upslope side, pooling in the soil, increasing the moisture content locally, creating temporary saturation. The pressure head increases. Water seeks a path through or around the obstacle. Some water flows around the log's ends, where the barrier does not extend across the full width of the hill slope. Some water percolates through the log itself. The log is porous, its structure riddled with passages created by beetles, by termites, by fungal decay. Water enters these passages, flows through the degraded wood, emerges on the downslope side. The flow through the log is complex. The passages are irregular, interconnected in 3 dimensions, sometimes blocked by intact wood. Water moves through the open passages, following whatever path exists, gradually working through the obstacle. The transit time is perhaps minutes to hours, depending on the exact path encountered. Emerging from the log, water continues downslope through the soil. The accumulation of many such flows, from many pathways, from a wide area of hill slope, creates measurable discharge, significant water movement, lateral flow that will eventually reach a topographic depression where surface water collects. Time is difficult to measure in this slow seepage. The flow rate of 10 micrometers per second means travel of 36 millimeters per hour, less than a meter per day. Covering 10 meters of hill slope distance requires more than 10 days at this rate. But the flow is not uniform. Fast paths through root channels and log passages reduce the average transit time. The actual time from forest floor to seep might be hours to days rather than weeks. Temperature remains constant throughout this journey. The soil temperature is buffered by the thermal mass of earth and vegetation, by the insulating effect of the leaf litter and canopy above. The temperature holds steady at 25 degrees Celsius. No thermal gradients exist to complicate the flow dynamics. The flow is isothermal, driven purely by gravitational potential and capillary forces. The chemistry is changing. The water, initially pure rainwater with only dissolved gases and trace salts from the original sea salt nucleus, is now acquiring dissolved minerals. Carbonic acid formed from dissolved CO2 reacts with minerals in the soil. Calcium, magnesium, potassium, sodium all leach into the water in trace amounts. Organic acids from decomposing matter add complexity. The water is no longer pure H2O, but a dilute solution, a complex mixture that will become even more complex as it continues through the soil system. The water approaches a region where bedrock rises close to the surface. The soil thins, the flow is forced toward the surface, toward emergence into air again. A seep is forming, a place where subsurface flow becomes surface flow, where water returns to visibility. Water returns to light and air. The emergence is gradual. The soil becomes progressively wetter as bedrock forces flow toward the surface. Finally, at an exposure of weathered rock, the water seeps out, emerges as a trickle, becomes visible again after its subsurface journey. The seep face is approximately 2 meters tall, nearly vertical, composed of metamorphic rock weathered into irregular shapes. The rock is grey-brown, mottled with lichens and algae, perpetually wet from the seepage. Water emerges from multiple points along the face where soil overlies rock, where pore spaces connect to the surface. The flow is gentle. Each seep point produces only a thin film of water, a few microliters per second, barely visible. But the accumulated discharge from dozens of seep points creates measurable flow, a combined discharge of perhaps 1 liter per hour from this 2-meter section of seep face. The rock surface is textured. Mineral crystals protrude in some areas. Weathering has created small pockets and channels in others. The water flows over and through this texture, spreading into a thin sheet, moving downward under gravity at perhaps 5 millimeters per second. Lichens cover much of the rock surface. These composite organisms, fungi and algae in symbiotic partnership, are adapted to the constant moisture, to the low light, to the dilute nutrients in the seeping water. The lichens form crusty patches, grey-green in colour, a few millimeters thick. Some are foliose lichens with leaf-like lobes. Some are crustose, tightly adhered to the rock. All photosynthesize when wet and light is available, growing imperceptibly slowly, contributing to the rock's weathering through chemical processes. Moss grows in thicker patches where water flow is concentrated. The moss is dark green, lush, formed of tiny stems with small leaves, creating miniature forests at the millimeter scale. Each moss plant is independent, but grows in dense mats, collectively holding water, maintaining moisture, providing habitat for microscopic animals, mites, tardigrades, rotifers, that inhabit the water films within the moss. The water passes through a moss patch. The individual moss stems, each less than a centimetre tall, create obstacles to flow. The water weaves between stems, flows over leaves, is briefly absorbed into the moss tissue before being released. The transit time through a patch of moss increases from seconds to minutes, but the flow continues, emerging from the downslope edge of the moss patch, resuming its descent. A tiny red mite is drinking at the base of the moss. The mite, approximately half a millimetre long, belongs to the family Erythraeidae, predators of small arthropods. It positions itself at the water's edge, its mouthparts extended, drinking directly from the flow. The mite requires water, cannot survive long without it, and this seep provides a reliable source. The water flowing past the mite includes the very molecules that fell as rain, that percolated through soil, that emerged here at this seep. Some molecules are drawn into the mite's digestive system, become part of its body water, temporarily removed from the free flow. The seep water is slightly acidic, pH approximately 5.5, a consequence of dissolved carbon dioxide and organic acids. The acidity helps dissolve minerals from the rock, contributing to chemical weathering, slowly eroding the seep face. Calcium carbonate, where present in the rock, is particularly vulnerable, dissolving more rapidly than other minerals, creating differential weathering patterns. The trickles from individual seep points converge as they descend. Small rivulets merge into larger ones. By the base of the seep face, the scattered emergence points have combined into a single small stream, perhaps 2 centimeters wide, flowing at approximately 10 centimeters per second, carrying the accumulated discharge from the entire seep face. The stream flows onto soil at the base of the rock face, but the soil here is saturated, unable to absorb more water. The stream continues as surface flow, following the steepest descent, carving a minute channel through the leaf litter, a path perhaps 3 centimeters wide and 1 centimeter deep. This is the birth of a stream. Downstream, this trickle will be joined by other seeps, other springs, other contributions from the hill slope. The flow will increase, the channel will deepen. A creek will form, then a larger stream, then eventually a river. But here, at the point of emergence, the stream is tiny, barely significant, yet essential. All rivers begin as seeps and springs, as small emergences that combine into larger flows. The stream flows through leaf litter, over exposed roots, between rocks. The path is irregular, meandering slightly even at this small scale. The flow is visible now, a silver line of moving water, catching what little light penetrates to the forest floor. Insects inhabit this nascent stream. Water striders skate on the surface, their hydrophobic leg tips supported by surface tension. Springtails leap from damp soil to the stream's edge, risk brief contact with water. Mosquito larvae may be present if the flow is slow enough to allow standing water. The aquatic community is forming, simple at this scale, but growing more complex as the stream grows downstream. The stream enters a slightly steeper section. The flow accelerates. The surface becomes rippled, tiny wavelets forming and dissipating as the water flows over small obstacles. The sound of flowing water becomes barely audible, a soft whisper, the first acoustic expression of the stream's existence. Current carries water downstream. This is flowing water now, not seepage, not soil moisture, but active surface flow in a defined channel. The transition is complete. The water has returned to the surface, joined the stream network, begun the final phase of its journey through the forest. The stream bed composition reveals the stream's history. Fine sediment, silt and clay, accumulated during low flow periods, deposited gently as water velocity dropped. Sand accumulated during moderate flows, transported along the bed as bedload. Occasional larger particles, gravel, small pebbles, moved only during high flows, during storms, when stream power was sufficient to dislodge and transport them. The sediment is stratified. Layers of different composition stack vertically, recording different flow regimes. A layer of fine silt, then a layer of sand, then another layer of silt, each representing a different event, a different rainfall, a different season. The stratigraphy is a record, readable by those who understand sedimentology, telling the stream's story. Organic matter mixes with mineral sediment. Leaves fallen into the stream settle onto the bed, accumulate, are slowly buried by mineral sediment. Woody debris, small twigs, fragments of bark, lies on the bed surface, too buoyant to be buried, but too heavy to be transported by current flow. This organic matter is food for decomposers, for shredders, for the base of the stream food web. The stream supports a complex community of macroinvertebrates. Mayfly nymphs cling to rocks, grazing on algae and diatoms. Caddisfly larvae construct portable cases from sand grains and organic fragments, carrying their homes as they move across the stream bed. Stonefly nymphs hunt among the stones, predators feeding on smaller invertebrates. Aquatic beetle larvae swim in the water column, also predatory, capturing prey with powerful mandibles. Each species occupies a specific niche. Some feed on algae, scraping it from rock surfaces with specialized mouthparts. Some shred fallen leaves, breaking large particles into smaller fragments. Some filter fine organic matter from the water column, using specialized setae or nets to capture particles. Some prey on other invertebrates, occupying the role of secondary consumers. The diversity is high, dozens of species in a few meters of stream length, each contributing to ecosystem function. Fish occupy the larger pools. The stream is too small for large fish, but small species thrive. Characins, just a few centimeters long, school in groups of 10 or 20, feeding on drifting insects. A small catfish, perhaps 5 centimeters long, hides beneath a rock, emerging at night to feed on invertebrates. These fish are part of the aquatic food web, connecting the invertebrates to larger predators. Birds, otters, larger fish downstream. The stream receives nutrients from multiple sources. Dissolved organic carbon leached from leaves and soil provides energy for bacteria and fungi. Nitrogen enters as ammonium, as nitrate, released by decomposition or washed from upslope. Phosphorus, often limiting in tropical ecosystems, enters primarily as particulate organic phosphorus in leaves, gradually mineralized by decomposition. These nutrients support primary production, algae and diatoms growing on rocks, converting sunlight and dissolved nutrients into biomass. The water chemistry reflects the forest's influence. The water is slightly acidic, pH approximately 5.5, from organic acids. Dissolved organic carbon concentration is high, perhaps 10 milligrams per litre, giving the water its tea colour. Calcium and magnesium concentrations are low. Tropical weathering has long since leached these base cations from the soil. The water is soft, low in total dissolved solids, very different from streams in limestone regions or temperate zones. The stream's temperature regime is stable. Shaded by forest, protected from direct sun, the water temperature stays close to ambient air temperature, approximately 26 degrees Celsius. There is no daily temperature cycle as in open streams where solar heating causes afternoon warming. The stability benefits organisms adapted to constant temperatures, allows species diversity to be high because thermal stress is low. Dissolved oxygen concentrations are high in the riffles, lower in the pools. In the riffles, turbulent flow entrains air, dissolves oxygen, maintains concentrations near saturation, perhaps 7 milligrams per litre at 26 degrees Celsius. In the pools, decomposition of organic matter consumes oxygen, reducing concentrations to perhaps 5 milligrams per litre, still sufficient for fish and invertebrates, but measurably lower. The oxygen gradient creates habitat diversity, some species preferring the well-oxygenated riffles, others tolerating the lower oxygen of pools. The stream is approximately 5 centimeters wide, 2 centimeters deep, flowing through a slight depression in the forest floor. The banks are leaf litter and exposed roots. The bed is a mixture of dead leaves, small twigs, and patches of mineral sediment, sand and silt carried from upslope by previous flows. The flow velocity is approximately 20 centimeters per second in the center of the channel, slower near the banks where friction is greater. The water molecules tumble in this flow, rotating, rising to the surface, then sinking to the bed, their paths chaotic in detail, but statistically constrained by the channel boundaries. This is turbulent flow, characterized by eddies, by mixing, by the constant exchange of momentum between adjacent parcels of water. The stream makes sound. The sound is quiet, barely louder than ambient forest noise, but distinct. It is the sound of water flowing over obstacles, of small ripples splashing against banks, of turbulence dissipating energy as acoustic vibrations. The frequency spectrum is broad, covering the range of human hearing but weighted toward mid-frequencies, the gentle burbling characteristic of small streams. A millipede crosses the stream. The arthropod, approximately 5 centimeters long, dark brown with dozens of legs, approaches the water, hesitates, then enters. The millipede is not aquatic but can tolerate brief immersion. It walks across the stream bed, its legs gripping the substrate, resisting the current. The flow is not strong enough to dislodge it. In 5 seconds, the millipede reaches the far bank, exits the water, continues its path through the litter. The stream encounters a root protruding across the channel. The root belongs to a large tree nearby, extending outward from the trunk, exposed where flowing water has eroded the soil around it. The root is perhaps 3 centimeters in diameter, covered in bark, creating a small waterfall as the stream flows over it. The water accelerates as it approaches the root, compressed into a narrower cross-section. At the root's crest, the water surface drops sharply, perhaps 5 centimeters, creating a small, free-falling curtain of water. The plunge pool at the base of the fall is slightly deeper, scoured by the impact of falling water. The water froths briefly with entrained air, then settles back into regular flow downstream of the root. A leaf falls into the stream. Fresh from the canopy, knocked loose by wind or an animal, the leaf lands flat on the water surface. Surface tension supports it briefly. The leaf is carried downstream by the current, riding the surface like a small boat spinning slowly in an eddy. The flow rate is approximately 20 centimeters per second. The leaf travels 2 meters in 10 seconds before snagging on a twig and coming to rest. The stream receives a tributary. Another small stream, emerging from a seep perhaps 50 meters upslope, joins from the left bank. The confluence is marked by a brief zone of mixing where the two flows meet, where turbulence increases temporarily. The combined stream is wider, 10 centimeters, and slightly deeper, 3 centimeters. The discharge has approximately doubled. With increased discharge comes increased erosive power. The stream is now capable of transporting larger particles. Fine sand grains, previously stationary on the bed, begin to move, rolling and bouncing downstream. This is bedload transport, the movement of particles along the bed rather than suspended in the flow. The transported sediment will eventually be deposited downstream in a location where flow velocity decreases. The stream channel deepens slightly. The flowing water is eroding the bed, cutting through the leaf litter into the mineral soil beneath. The erosion is slow, perhaps millimeters per year, but cumulative over years and decades. The channel evolves, deepens, widens, adjusts its form to carry the water and sediment supplied from upslope. A dragonfly nymph clings to a submerged stick. The nymph is approximately 2 centimeters long, brown-green, with a robust body and powerful legs. It is a predator, waiting for smaller insects to pass within striking range. The nymph's lower jaw is modified into a hinged labium, capable of shooting forward to capture prey. The nymph can remain motionless for minutes, patient, camouflaged, an ambush predator in the stream's microhabitat. The stream flows through a section where bedrock is close to the surface. The channel here is shallower, wider, flowing over smooth rock rather than soil. The flow is faster, the turbulence greater. This is a riffle, a shallow, fast-flowing section characterized by a rough water surface, by splashing, by high oxygen content in the water. Oxygen enters the water primarily through the air-water interface. Turbulence increases the surface area of that interface, creating more opportunity for gas exchange. In the riffle, oxygen dissolves into the water from the air, increasing the dissolved oxygen concentration to near saturation. This oxygenation supports aquatic life, provides the dissolved gas that fish and invertebrates require for respiration. Downstream of the riffle, the channel deepens. The bedrock dips below the surface. Soil and sediment accumulate here, creating a pool, a deeper, slower section. The pool is perhaps 30 centimeters wide, 15 centimeters deep. The flow velocity drops to 5 centimeters per second. The water surface is smooth, no longer rippled, reflecting the forest canopy above. Pools and riffles form a natural sequence in streams. Riffles occur where the channel gradient is steep or bedrock is close to the surface. Pools form where gradient is gentle or sediment accumulates. The sequence repeats at intervals related to channel width, typically 5 to 7 channel widths between successive riffles. This spacing is not random, but arises from the physics of flowing water, from the interaction between flow, sediment transport, and channel morphology. A small fish rests in the pool. The fish is a characin, perhaps 5 centimeters long, with silver scales and a forked tail. It holds position in the slow current, fins making small adjustments, maintaining its place in the water column. The fish is feeding on insects, mayfly nymphs, midges, that drift in the current. When a prey item passes, the fish darts forward, captures it, returns to its holding position. The stream continues downstream, growing with each tributary, each seep, each contribution from the hill slope. The forest guides the water, channels it, directs it toward the valley bottom where larger streams form, where water from multiple hill slopes combines into a significant flow. Multiple tributaries merge into deeper water, feeding flows bigger than them. The stream is now a creek, a third-order stream in the Strahler system of stream classification, formed by the merger of second-order streams, each of which formed from first-order streams. The hierarchy of the drainage network is becoming evident. The creek is approximately half a meter wide, 20 centimeters deep in pools, 10 centimeters deep in riffles. The flow velocity varies from 5 centimeters per second in pools to 30 centimeters per second in riffles. The discharge is approximately 20 liters per minute, substantial enough to create a permanent stream, one that flows year-round, fed by groundwater during dry seasons, by direct runoff during wet seasons. The channel is carved into soil and weathered rock. In some sections, the creek has incised down to bedrock, creating a small gorge, perhaps 1 meter deep, with vertical rock walls. In other sections, the channel meanders through soil, with gentle banks, with roots extending into the water from trees on either side. The water is clear, slightly tea-coloured from dissolved organic compounds leached from decomposing leaves. The colour is subtle, barely noticeable in small quantities, but visible when looking through tens of centimetres of water depth. The tannins and humic acids that create this colour also affect water chemistry, slightly lowering pH, slightly increasing dissolved organic carbon. Fish are more abundant here than in the smaller stream upstream. Characins school in the pools, perhaps a dozen individuals ranging from 3 to 10 centimetres in length. These fish feed on drifting insects, on algae growing on rocks, on small invertebrates. A larger fish, perhaps a cichlid, patrols a section of the creek, defending territory, chasing away intruders. The fish community is structured, with species occupying different niches, competing for resources, coexisting through partitioning of habitat and food. A fallen log spans the creek. The log is perhaps 40 centimeters in diameter, 3 meters long, lying where it fell years ago when the tree died and collapsed. The log is partially submerged, its upstream side collecting debris, leaves, twigs, small branches, carried downstream by the current. This debris dam creates a small pool upstream where water backs up, slows, deepens. The log itself is habitat. Insects burrow in the decaying wood. Fish hide beneath the log in the shadow, protected from predators. Salamanders might take shelter in crevices in the bark. The log is an ecological structure, contributing to biodiversity, to habitat complexity, to the functioning of the stream ecosystem. Water flows over and under the log. Some flow passes over the top, creating a small waterfall on the downstream side. Most flow passes underneath, through the gap between log and stream bed. The flow accelerates in this constriction, scouring the bed beneath the log, creating a deeper channel. The accelerated flow then decelerates downstream of the log, depositing sediment, creating a bar of sand and gravel. This sequence, pool, log dam, scour underneath, deposition downstream, is a common pattern in forested streams. Logs are abundant in natural forests, falling regularly as trees die. The logs shape the stream, creating habitat diversity, influencing sediment transport, affecting flow patterns. A tributary enters from the right. The tributary is similar in size to the main channel, perhaps 40 centimeters wide. The confluence is marked by a zone of mixing, where the two flows meet at an angle, where turbulence increases, where patterns of surface disturbance reveal the merging currents. The combined flow is noticeably larger, 1 meter wide, 25 centimeters deep, discharge approximately 40 liters per minute. The sound of the creek is louder now. The increased flow, the larger obstructions, the more frequent riffles, all contribute to greater acoustic output. The sound is a continuous background now, not the quiet whisper of the small stream, but the fuller voice of a creek in moderate flow. The frequency spectrum is still broad, but the intensity is greater, audible from meters away. The forest structure is different here in the valley bottom. The creek occupies a slight depression, a drainage way, where water accumulates, where soil moisture is higher than on adjacent hill slopes. The vegetation responds. Species that tolerate periodic flooding dominate. Trees have stilt roots or other adaptations. Palms are abundant. The understory includes ferns and moisture-loving herbs. The creek encounters a section where bedrock rises, creating a small rapid. The water flows over smooth rock, accelerating, becoming turbulent, splashing loudly. The rapid is perhaps 3 meters long, with a drop of approximately 30 centimeters. The flow velocity in the rapid reaches 50 centimeters per second. The water is white with entrained air, oxygenated by the turbulence. Downstream of the rapid, the creek enters a quiet pool. The pool is large, 2 meters wide, half a meter deep, formed where the channel widens, where velocity decreases, where sediment settles. The pool is a refuge for fish, a nursery for juveniles, a habitat for species that prefer still water. The contrast between the rapid and the pool illustrates the habitat diversity created by natural variation in channel gradient and morphology. A turtle basks on a rock at the pool's edge. The turtle is medium-sized, perhaps 20 centimeters shell length, dark brown with faint yellow markings. It is absorbing heat from the dim light, raising its body temperature above the ambient 26 degrees, increasing its metabolic rate, improving its ability to hunt and digest food. The turtle is adapted to the forest stream, spending most of its life in or near water, feeding on fish, insects, and carrion. The creek continues downstream, more tributaries join. The channel deepens, the flow increases. The creek is transitioning toward a small river, though the transition is gradual, without a definite threshold. The water continues its journey, always downslope, always seeking lower elevation, moving toward the valley's lowest point. The rushing slows to drifting. The creek has descended from the hill slope to the valley floor. The gradient, the slope of the channel, decreases from steep to gentle. The flow velocity decreases proportionally. What was rapid flow becomes slow meandering. The character of the stream changes completely. The channel widens and shallows. Where the creek was 1 meter wide and 25 centimeters deep, it now spreads to 2 meters wide and 15 centimeters deep. The flow velocity drops from 20 centimeters per second to 5 centimeters per second. The water moves, but slowly, gently, almost imperceptibly. The banks are barely defined. The channel merges gradually with the surrounding wetland. During high water, the creek overtops its banks, floods the adjacent forest floor, deposits sediment, creates a small floodplain. The vegetation reflects this flooding history. Flood-tolerant species dominate: palms with pneumatophores, trees adapted to waterlogged soil, herbs that grow rapidly when exposed after floods. Aquatic plants grow in the channel itself. These are true aquatic species, not terrestrial plants tolerating wet conditions, but plants adapted to life submerged or floating. Pondweeds grow from the bed, their stems reaching toward the surface, their leaves sometimes floating, sometimes submerged. Water hyacinths may be present if conditions are right, their floating leaves and purple flowers visible on the surface. The presence of aquatic plants indicates slow flow, stable conditions, sufficient light. In faster flowing sections, plants cannot establish. The current would uproot them, the turbulence would tear their leaves. But here, in the slow water of the valley floor, plants can grow, can photosynthesize, can contribute to the ecosystem as primary producers. A dragonfly perches on an emergent stem. The adult dragonfly, approximately 8 centimeters long with iridescent blue-green coloring, has recently emerged from its aquatic nymphal stage. It is now an aerial predator, hunting mosquitoes and other flying insects. But its life cycle remains tied to water. It will eventually mate, and the female will lay eggs in the stream, beginning the cycle again. The water is warmer here than in the upstream creek. The increased exposure to sunlight, the slower flow, the shallower depth, all contribute to warming. The temperature has risen to 28 degrees Celsius, 2 degrees above the ambient forest temperature. This warming has ecological consequences. Warm water holds less dissolved oxygen. The oxygen concentration has dropped from near saturation in the upstream riffles to perhaps 70% saturation here in the slow water. Fish species reflect this change in oxygen availability. The characins of the upstream pools are less abundant here. Species adapted to low oxygen dominate instead. Fish capable of supplementary air breathing, species with efficient oxygen extraction mechanisms, species tolerant of hypoxic conditions. The stream channel splits. Multiple small channels form, separated by vegetated islands. This is braiding, a channel pattern that occurs where sediment is abundant, where flow velocity is insufficient to maintain a single deep channel, where the stream spreads out across the available width. The water molecules are distributed among these channels, some following one path, some another, but all moving generally downstream toward the same destination. One channel leads through dense vegetation, aquatic plants so thick they almost block the flow. The water moves through this vegetation at perhaps 1 centimeter per second, barely perceptible. The plants filter the water, their stems and leaves creating resistance, slowing flow, trapping fine sediment. Another channel follows a more open path, with less vegetation, faster flow. Water here moves at 10 centimeters per second, still slow compared to upstream but faster than through the vegetated channel. The channels will eventually reconverge downstream, the water mixing again, the split temporary. A wetland extends on both sides of the stream. The wetland is a low-lying area where water accumulates, where the water table is at or near the surface, where standing water persists between rain events. The vegetation is distinctive: palms, sedges, water-loving shrubs. The soil is permanently saturated, gleyed, grey in colour from anaerobic conditions, enriched with organic matter. The wetland is productive. Algae grow in the sunlight, performing photosynthesis, producing oxygen during the day, consuming it at night. Aquatic plants contribute as well. Decomposition is active, bacteria and fungi breaking down the abundant organic matter, releasing nutrients, supporting a complex food web. Mosquitoes are abundant. Their larvae hang from the surface film, filtering food particles, developing rapidly in the warm water. Adult mosquitoes swarm in shaded areas, seeking blood meals from warm-blooded animals. Dragonflies and damselflies hunt the mosquitoes, keeping populations in check but not eliminating them. The stream channels reconverge. The braided pattern gives way again to a single channel, slightly larger than before, approximately 3 meters wide. The flow continues downstream, approaching a more permanent body of standing water, a pond or small lake, the ultimate destination for this particular path through the forest. Flow ceases in standing water. Of course, that water doesn't need legs to stand, but stays still. The creek enters a pond, and the transformation from moving to still water is abrupt. Velocity drops from 5 centimeters per second to effectively 0. Momentum dissipates. Current disappears. The water has entered a different regime, a different ecosystem, a body of water where residence time is measured in days rather than minutes. The pond is approximately 50 meters across, 3 meters deep at its center, surrounded by forest. The pond is natural, formed in a topographic depression, fed by the creek and other seeps, draining through an outlet on the downstream side. The water level fluctuates with rainfall, rising during wet periods, falling during dry periods, but never emptying completely. The creek water enters the pond as a plume. The inflowing water has momentum, carries sediment, differs in temperature and chemistry from the pond water. The plume extends several meters into the pond before dissipating, before mixing fully with the standing water. The transition is visible if turbidity is different, invisible if not. The water molecules that were moving downstream in the creek are now dispersed in 3 dimensions. They spread laterally, they sink or rise depending on density differences. They mix gradually through diffusion and convection. The concept of downstream no longer applies. There is no preferred direction, no flow to follow. The water simply exists in the pond, part of the volume, subject to the physical processes that govern standing water bodies. The pond is stratified. The surface layer, the epilimnion, is warm, approximately 30 degrees Celsius, heated by solar radiation, mixed by wind. The bottom layer, the hyperlimnion, is cooler, approximately 25 degrees, isolated from surface heating, cooled by contact with the soil below. The boundary between these layers, the thermocline, is a zone of rapid temperature change, occurring at approximately 1 meter depth. The pond ecosystem is stratified not just thermally, but chemically and biologically. The surface waters, warm and well lit, support high photosynthetic rates. Phytoplankton bloom here, reaching concentrations of millions of cells per litre. The primary producers are diverse: green algae like chlorella and cenodesmus, diatoms with their silica shells, cyanobacteria capable of nitrogen fixation. Each group occupies a slightly different niche, some preferring nutrient-rich conditions, others thriving in low-nutrient environments, creating a complex assemblage. The phytoplankton growth is limited by nutrients. Nitrogen and phosphorus are typically the limiting nutrients in tropical ponds. Nitrogen enters through rainfall, through fixation by cyanobacteria, through decomposition of organic matter. Phosphorus enters primarily through erosion, through the breakdown of organic matter, through runoff from the watershed. The ratio of nitrogen to phosphorus affects which species dominate. High NP ratios favour diatoms, low ratios favour cyanobacteria. Zooplankton graze on the phytoplankton. Rotifers, tiny multicellular animals barely visible to the naked eye, spin through the water using ciliated wheels, filtering algae from the water. Copepods, small crustaceans with segmented bodies and jointed appendages, capture algae with specialized feeding appendages. Cladocerans, like Daphnia, filter algae non-selectively, consuming whatever particles fall within a certain size range. The grazing pressure from zooplankton can control phytoplankton biomass, preventing algal blooms from becoming excessive. The zooplankton themselves are food for larger predators. Fish larvae feed on rotifers and small copepods. Adult fish feed on larger cladocerans and copepods. Predatory zooplankton, like the phantom midge larvae, transparent predators that are nearly invisible in water, feed on other zooplankton. The food web is complex, with multiple trophic levels, energy flowing from sunlight through phytoplankton, through zooplankton, through fish. The thermocline creates a barrier to mixing. Nutrients released by decomposition in the hyperlimnion remain trapped below the thermocline, unavailable to phytoplankton in the surface waters. This nutrient trapping is characteristic of stratified water bodies. It creates a gradient: nutrient-poor surface waters, nutrient-rich bottom waters. The metalimnion, where the thermocline exists, becomes a zone of high productivity because nutrients diffusing upward meet light, penetrating downward. Certain organisms specialize in this metalimnion zone. Photosynthetic bacteria, particularly purple sulfur bacteria, can photosynthesize using wavelengths of light that penetrate to this depth, infrared and far red, and using hydrogen sulfide, produced by decomposition below, as an electron donor instead of water. These bacteria form layers at the thermocline, visible as pink or purple bands if the pond is viewed in cross-section. The diurnal cycle creates rhythms in the pond. During the day, phytoplankton photosynthesize, producing oxygen, sometimes supersaturating the surface waters. During the night, respiration by all organisms, phytoplankton, zooplankton, fish, bacteria, consumes oxygen, drawing down concentrations. By dawn, oxygen concentrations may be significantly lower than at dusk. Fish and other organisms must cope with this daily oxygen variation. Zooplankton migrate vertically daily in response to predation pressure and food availability. At night, they rise to the surface to feed on phytoplankton, taking advantage of darkness to avoid visual predators like fish. At dawn, they descend to deeper waters, trading off feeding opportunity for predator avoidance. This diel vertical migration is one of the largest animal migrations on Earth by biomass, occurring in ponds, lakes and oceans worldwide. The pond bottom is anoxic. Dissolved oxygen is zero. In this environment, anaerobic bacteria dominate. Sulfate-reducing bacteria use sulfate as an electron acceptor, producing hydrogen sulfide. Methanogenic bacteria produce methane from organic matter. Denitrifying bacteria convert nitrate to nitrogen gas. These anaerobic processes alter the chemistry of the sediment and the overlying water, creating conditions very different from the oxygenated surface. Methane produced in the sediment sometimes bubbles to the surface. Small bubbles rise through the water column, visible as streams of bubbles emerging from the bottom. The methane is a greenhouse gas, its release from aquatic sediments contributing to atmospheric methane concentrations. Tropical ponds and wetlands are significant methane sources globally. The pond's edge, the littoral zone, is distinct from the open water. Aquatic plants grow here, rooted in shallow sediment. Emergent plants like reeds and sedges grow with roots underwater, but leaves above water. Floating plants like water lilies have roots in sediment but leaves on the surface. Submerged plants grow entirely underwater, photosynthesizing while submerged. Each zone supports different communities: insects on emergent plants, snails on floating plant undersides, small fish among submerged vegetation. The water molecule, circulating through this complex system, experiences all these zones over time. Rising from the bottom hyperlimnion during nighttime convection, crossing the thermocline, entering the productive epilimnion, mixing among phytoplankton and zooplankton, drifting toward the littoral zone, returning to deeper water. The residence time in different zones varies, but the average residence time in the pond, approximately 2 weeks, ensures thorough mixing eventually. Stratification affects chemistry. The warm surface water is in contact with the atmosphere, exchanges gases readily, maintains high oxygen concentrations. The cool bottom water is isolated, relies on what oxygen was present when stratification formed, or on what little mixing occurs across the thermocline. Oxygen concentrations in the hyperlimnion are lower, sometimes approaching anoxia. Light penetration is limited. The water is tea-coloured from dissolved organic matter. Algae in the water column scatter light. The light intensity decreases exponentially with depth. At 1 metre depth, only 10% of surface light remains. At 2 metres, only 1%. At 3 metres, photosynthesis is impossible. The bottom is dark, relying on organic matter settling from above, on chemosynthetic bacteria adapted to low oxygen and no light. Phytoplankton blooms in the lit surface waters. These microscopic algae, green algae, diatoms, cyanobacteria, photosynthesize using sunlight and dissolved nutrients. They are the base of the pond's food web, converting solar energy into biomass, supporting zooplankton, which support fish, which support larger predators. The productivity is high in tropical ponds, limited more by nutrients, particularly nitrogen and phosphorus, than by light or temperature. Zooplankton drift in the water column, copepods, cladocerans, rotifers. These tiny animals, typically less than 2 millimeters long, feed on phytoplankton or each other. They migrate vertically daily, near the surface at night to feed, deeper during the day to avoid visual predators like fish. This migration creates a daily cycle of vertical mixing, transporting nutrients and organic matter between layers. A water molecule from the inflowing creek drifts through this environment. Initially near the surface, in the warm epilimnion, it slowly mixes through the water column. Over days, it sinks, carried by weak downward currents, settling gradually toward the thermocline. The mixing is slow, driven by diffusion and convection, not by active flow. Fish are abundant. Small characins school near the surface, feeding on insects that fall onto the water. Cichlids patrol the bottom, turning over sediment, hunting for invertebrates. A larger predatory fish, perhaps a snakehead or catfish, lurks in the shadows, ambushing prey. The pond supports a diverse fish community, dozens of species, each occupying a particular niche. Insects swarm at the surface. Water striders skate on the surface film. Whirligig beetles gyrate in circles, hunting prey. Mosquitoes emerge from larvae, dry their wings, fly off to find blood meals. Dragonflies patrol overhead, capturing flying insects, returning to perches on emergent vegetation. The pond bottom is covered with sediment. Fine particles, clay, silt, organic matter, have settled from the water column, accumulating over years into a layer perhaps 20 centimeters thick. The sediment is anoxic, black, smelling of hydrogen sulfide. Bacteria thrive here, decomposing organic matter in the absence of oxygen, using nitrate or sulfate as alternative electron acceptors. The water molecule continues mixing through the pond volume. Time passes. Hours, days. The molecule circulates through the epilimnion, crosses the thermocline, enters the hyperlimnion. Temperature changes from 30 degrees to 25 degrees. Oxygen concentration drops from saturation to near zero. Light disappears. The molecule is in the dark bottom water now, part of the anoxic zone. But eventually, currents carry the molecule back toward the surface. Convection, driven by nighttime cooling, mixes the water column. The molecule rises, crosses the thermocline again, returns to the warm oxygenated surface layer. The residence time in the pond is finite. Water enters through the creek and seeps. Water leaves through the outlet. The average residence time is perhaps 2 weeks, but individual molecules may stay days or months, depending on the exact path they follow. The outlet beckons. The pond drains through a spillway on the downstream side, a natural low point where water flows out when pond level is high. The water molecule, circulating through the pond volume, eventually approaches this outlet region. The approach is gradual. No strong current exists to carry water directly from inlet to outlet. The movement is by diffusion, by weak convection currents, by the slow circulation patterns established by wind and thermal gradients. Over days, the molecule drifts across the pond, closer to the outlet. Near the outlet, a weak current becomes evident. Water is leaving through the spillway, creating a flow field, drawing water from the surrounding pond volume. The current is perhaps 1 millimeter per second, barely perceptible, but sufficient to create preferred flow paths to direct water toward the outlet. The spillway is a notch in the natural dam that forms the pond. The notch is perhaps 1 meter wide, with water flowing over a lip of soil and rock. The water depth in the spillway is approximately 10 centimeters. The flow velocity is 30 centimeters per second, faster than anywhere else in the pond. The transition from pond to outlet stream is dramatic. The calm water of the pond gives way to the flowing water of the outlet. Velocity increases from near zero to 30 centimeters per second in the span of a few meters. The water accelerates, drawn by gravity, pulled downslope by the hydraulic gradient. The outlet stream flows over a small waterfall, dropping perhaps 30 centimeters from the pond level to the channel below. The water falls freely, splashes at the base, froths with entrained air. The impact creates turbulence, mixes the water thoroughly, oxygenates it, prepares it for the next phase of the journey. The molecule is carried through this transition, from drifting in the pond to approaching the outlet, to accelerating through the spillway, to falling over the waterfall. The transformation takes less than a minute. The molecule is flowing again, back in a stream, descending through the valley, continuing its journey downslope. The forest channels water toward the river, almost feeding it. The outlet stream flows through forest, joining with other streams, growing in volume and power. The water molecules are part of this growing flow, indistinguishable now from the rest of the stream water, just molecules in the collective, moving downstream under gravity's inexorable pull. The stream enters a larger stream. Then that stream enters a small river. The river is wide, several meters across, deep, powerful, carrying water from hundreds of square kilometers of forest. The flow is substantial, measured in cubic meters per second. The river is a major feature of the landscape, a transportation corridor, a source of fish and water, an ecological artery. The river flows through lowlands, through floodplains, meandering in great loops, occasionally cutting through to create oxbow lakes. The journey from forest stream to river mouth may take days or weeks, covering tens or hundreds of kilometers, descending hundreds of meters in elevation. Eventually, the river reaches the ocean. The fresh water meets salt water. The mixing zone, the estuary, is brackish, ecologically complex, highly productive. The water molecules that fell as rain in the forest, that descended through canopy and soil, that flowed in streams and ponded in lakes, now enter the ocean, completing one cycle, preparing for the next. In the ocean, the molecules will eventually evaporate. Rising into the atmosphere, they will condense in clouds, perhaps over the same forest, perhaps over distant continents. They will fall as rain again. The cycle will continue. The cycle continues without end, moving up and down with admirable persistence, from ocean to atmosphere to rain to forest to stream to river to ocean again. The transformations are constant. The movement is perpetual. The rainforest participates intimately in this cycle. Each day, billions of liters of water evaporate from leaves, returning moisture to the atmosphere. Each day, rain falls, replenishing soil moisture, feeding streams. The forest and the atmosphere are coupled, each influencing the other, creating a regional climate, maintaining the conditions that allow the forest itself to exist. This water molecule may remain in the region, cycling locally between forest and atmosphere, falling and evaporating repeatedly. Or it may be carried away by winds, transported across continents, falling as rain in distant locations. The residence time in different reservoirs varies. Days in the atmosphere, weeks in rivers, years in groundwater, millennia in deep aquifers or ice sheets. But the cycle persists. Water evaporates, water condenses, water falls, water flows, water evaporates again. The cycle is as old as the oceans, as old as the atmosphere, dating back billions of years to when the planet first cooled sufficiently for liquid water to exist. The physics is simple. The sun provides energy. Evaporation requires that energy. Gravity pulls water downward. The cycle is driven by these two fundamental forces, solar energy and gravity, operating continuously as long as the sun shines and the planet retains its mass. The chemistry is simple too. H2O, two hydrogen atoms bonded to one oxygen atom. The molecule is stable, unchanged by the cycle. The water that falls today is the same water that fell 1,000,000 years ago, the same water that will fall 1,000,000 years hence. The molecules persist, the cycle continues. The forest depends on this cycle. Without rain, without the constant replenishment of moisture, the forest would die, would transform into savanna or desert, would lose the biodiversity, the productivity, the complexity that defines it as rainforest. Water is not merely present in the forest, it creates the forest, sustains it, defines it. The river system the raindrop enters is part of a vast network draining the rainforest. Thousands of small streams combine into hundreds of larger streams, which merge into dozens of rivers, which finally converge into one or a few major rivers flowing to the ocean. The network is dendritic, tree-like, shaped by millions of years of erosion, by the interplay of rainfall, topography, and geology. The river itself is a dynamic system. It floods seasonally, inundating adjacent forests, depositing sediment, creating floodplain ecosystems. It cuts new channels, abandons old ones, migrates laterally across the valley floor. The river is not static, but constantly changing, reshaping the landscape, responding to the water and sediment delivered from upstream. The water travelling down the river experiences transformations. Dissolved organic matter is consumed by bacteria, converted to bacterial biomass, incorporated into the food web. Suspended sediment settles in slow-flowing sections, is resuspended in fast-flowing sections, gradually working downstream toward the ocean. Nutrients are taken up by algae, converted to plant tissue, consumed by grazers, cycled through the aquatic ecosystem, before being released again. The journey from forest headwater to river mouth may take weeks. Water moves through pools where residence time is days, through rapids where transit time is minutes. The average velocity varies, perhaps 0.5 meter per second in the rainy season, perhaps 5 centimeters per second in the dry season. The river's flow responds to rainfall, rising during storms, falling during dry periods, fluctuating but never ceasing completely in perennial tropical rivers. As the river approaches the coast, it enters the estuary. Here, fresh water meets salt water. The mixing is complex, influenced by tides, by river discharge, by density differences between fresh and salt water. Salt water, denser, flows upstream along the bottom. Fresh water, lighter, flows downstream along the surface. The estuary is brackish, with salinity varying from near zero near the river mouth to near oceanic values near the coastal entrance. The estuary is highly productive. Nutrients delivered by the river meet the ocean's vast reservoir of marine organisms. Phytoplankton bloom in the nutrient-rich, brackish water. Fish, shrimp, crabs. Many marine species use estuaries as nurseries, their young growing in the protected, food-rich environment before moving to the open ocean. The estuary is a transition zone, ecologically and chemically, between terrestrial and marine systems. Finally, the water enters the ocean. The molecules that fell as rain in the forest, that descended through canopy and soil, that flowed in streams and ponded in lakes, now mix with the vast volume of seawater. The fresh water floats initially, less dense than salt water, forming a surface lens. But waves, currents, and turbulence eventually mix it downward, integrating it into the ocean's water column. In the ocean, the water will join the global thermohaline circulation. Perhaps it will sink in polar regions, becoming part of deep ocean currents flowing for centuries through the abyss. Perhaps it will remain in surface waters, circulating in ocean gyres, crossing the Pacific in years. Perhaps it will evaporate quickly, returning to the atmosphere within days, beginning the cycle again. The evaporation process in the ocean is similar to evaporation from leaves or ponds. Molecules at the surface gain sufficient energy from sunlight to break free from liquid phase. The energy requirement is the same, approximately 2.25 megajoules per kilogram. The vapor rises into the atmosphere, joins the water vapor already present, moves with winds, eventually condenses in clouds, falls as rain somewhere. That rain might fall on the same forest where the journey began. It might fall on distant continents, on mountains, on deserts, on other oceans. The probability of returning to the exact starting point is infinitesimally small. The forest covers perhaps hundreds of square kilometers. The planet's surface covers 500 million square kilometers. But the probability of returning to some rainforest somewhere in the tropics is higher. Tropical convection returns much moisture locally, creating the high rainfall that sustains the forests. The cycle continues. The rain falls, the water flows, always.